Hi, this is Mr. Merrill, and we're taking a look at another quantitative projectile motion problem. This one's a little bit more difficult because it involves some initial vertical velocity. So the question is, we're playing this carnival game. I'm flipping a coin into a bowl here at the top. I have some dimensions given. And the question is, how far away from the bowl should I stand for it to reach that position? And how high above where I release it does a coin reach? Okay, so how high above the ground, I should say, does a coin reach? So we'll look at those two problems, starting with the first one. But what you should do, regardless of the problem, is if you are given some initial velocity with an angle, you should use trig to break that initial velocity into components. So trying to draw your own components out and recognize that there's a y and an x is the first step there. So we have the length of this green side. We can use trig, cosine for the adjacent side and sine for the opposite, to find the values for the two components there. Both these components have to be positive because this points to the right and this points up. They are not necessarily always positive depending on the problem. So then we go back to the table that we constructed last time, recognizing that we're always caring about the same 7 quantities. They pop up with this projectile motion. We plug in what's given in the problem, either obviously given from the diagram or having to think about it a little harder to tease it out. So the first thing we can put in is our initial x velocity and y velocity. And we assume this takes place on Earth, so we can assume a constant downwards acceleration of negative 9.8 meters per second squared. And you might have a little more trouble with the vertical displacement, recognizing why is this 0.8? Well, because in the vertical direction, over the course of the trip, yes, it moves up some, yes, it moves down some, but if we think about from where it was released initially in the y direction to where it ends up initially at the end in the y direction, that's a displacement of 0.8 meters, meaning altogether it's moved up from its starting point 0.8 meters. And we really don't know anything else. So what we need to do is think about what we want. So it's asking for this distance here, which is essentially the x displacement, how far it moves in the x direction over this trip. So we have a very simple equation for that. The problem is that it depends on the initial x velocity, which we have, but it also depends on the time, the flight time, which we do not have. So that brings us to a secondary problem to first find the time. So now you have to look in the y direction to think about that. So why don't you pause for a moment and think about which equation you would choose in y. So I ended up choosing the first equation because we have this, we have this, we have this. The only thing we don't have is the time. So with only one unknown, I can solve it. So this is a quadratic, so we're not going to do our normal algebra, shuffling things around to solve for something on one side because it won't work. So we plug in our values just from our table, and do some distribution. I do some shuffling around. Basically what I want is a 0 on one side, and I drop the units here just to make it easier to look at. So we're left with this equation with a 0 on one side. You'll see why we want to do that. Well, now we're left with two options. I can either use the quadratic formula to solve this, or what I personally prefer to do is use a graphing calculator. So how do you do that? You simply open up your graphing calculator, and this is going to be different for inspires. I can't help you there. But you go to the y plot, and we punch in this value. So negative 4.9x squared plus 5.5426x minus 0.8. So I'm essentially saying y equals this. Why am I doing that? Because I want to find, if I set y equals to this right side here, then I can find out the situation where y equals 0, and I'm essentially finding the solutions to that, the t's that make that true. So I go ahead and graph it, and I can zoom in here. Maybe not. There we go, zoom in. And you'll see that we have two intersections. Now, how do we actually find those intersections? We'll go to second calc, 0, or you could use the intersection button. I'm going to find the second intersection here, and I'll talk about it. You can find both if you want to. So there's a bit of delay. So we just need something to the left of the intersection, and then it'll take a while for the cursor to catch up. Okay, and we get that for a value. Now it says x, but remember we're actually solving for time here. I could also do the other intersection, you'll get another value. But we need to understand why we're getting two values. So here are the two values, just from the calculator. Why does it make sense that the calculator would produce two values for time? Well, the question that we're asking is essentially, when does the displacement equal 0.8? As in, when is this coin 0.8 meters vertically from where it was released? And if you think about the path that this coin is going to take, it's going to follow a trajectory, something like this, obviously not perfectly drawn, some parabolic trajectory along the lines of that. Well, consider a line that passes through that vertical height 0.8. You're essentially going to have two times when it reaches that height. Once in the beginning on the way up, right here, that corresponds to this time, and then once on the end, right here on the way down, that corresponds to this time. So depending on the situation you have, you might have one, none, or two. But here we have two. Now, which one do we actually care about? The second one, because the second time corresponds to when it's actually landing in the bowl here. Alright, so we finally have our time. We can add that to our chart. And again, the end goal is to find delta x. So we simply go back to the equation that we first thought about, plug things in, and we find our displacement here should be 3.07616, and obviously you can round that off. Okay, so the next question is, how high above the ground does a coin reach? Now, even though we just did this with the bowl, you have to realize for this question, the bowl is irrelevant. It's not asking about that. What it's saying is, again, this coin is going to follow some trajectory. The question is, how far above the ground does a coin reach? It's essentially asking about this distance here, this maximum coin distance, how high above the ground that reaches. So you have to think about that as an entirely new problem. And the way to approach it is to realize that at the top here, at the highest point, there is not going to be any vertical velocity. The velocity in the vertical direction is going to be reduced up to its highest point and then increase on its way back down. So what does that do? That means this, which is not which is not stated in any part of the problem, we have to imply it, is going to be 0 at the top, at the highest point. However, don't make the mistake of thinking this is 0. This is still the same value that it always is. All I'm saying is that the top, it doesn't have a vertical component of the velocity. Alright, well that also changes things up too. Don't think that this is still what we calculated in the last problem, because it's not talking about the whole trip. It's just talking up until this point in the trip over here. So we have to treat it as a completely new problem is what I'm trying to get at. And the question being, what is this value? Or at least that's our starting point. I'll talk about how that's not the actual final answer. So anyway, let's find our delta y. You can think about an equation at this point of what you would want to use to find delta y. Okay, so the equation that I ended up picking was this third kinematics equation, and for the simple reason that, well, I know that the final y velocity is going to be 0, so that cancels out that term. But more importantly, I picked it because I know I know what this initial y velocity is, and I know what that acceleration is, so it leaves me with only one unknown, the unknown that I actually want to solve for. So I do a little bit of algebra, I rearrange in terms of delta y, and I solve out what delta y is here. Now, a lot of people will stop at that point, and they'll think that is the final answer. It's not the final answer. You have to understand what this delta y is. What delta y is it's the vertical distance the projectile has risen above its initial release. So delta y is this distance here, how high it's released. So at the top of the projectile, at the top of the arc there, it got that 1.576 meters above the ground at the top of the projectile there. But that's not what the question is asking. If you read it, it says how high above the ground down here does it release. So I have to add this additional meter. And the point of that question is just to make you differentiate in your mind between what delta y is, something specific to the particle, projectile, and what h is, something that's based on the situation around the projectile. So in the last projectile motion problem, I showed you a little bit easier way to solve the second part using energy. I'll do the same thing here. So let's answer the second part, not with projectile motion, but thinking about it in terms of energy. This question of how high above the ground does the coin reach? So the only thing that I have to realize to solve this problem is that when the coin is at its highest point, its velocity, its entire velocity, is just equal to its x component. What I mean by that is that this final velocity at the top here is essentially this 3.2 meters per second. That x component of the velocity that we calculated way back then. So we can think about it as starting out with just kinetic and gravitational energy. So we start out with some speed and some distance above the ground. I've gone ahead and defined this bottom ground line as h equals 0. And I end with a little bit less kinetic energy, but a little bit more gravitational potential energy, meaning I'm higher up, but I'm moving slower. So I'm missing a little plus sign here, but I take it down the equation, and then I see, plugging everything in here, I see the masses cancel out. Again, that makes sense. This is projectile motion. The masses should not matter. And I simply do some algebra to rearrange for h final, what I'm really looking for, the distance above the ground that it is at the end. And plugging in, you get the really satisfying answer that it works the same. You get the same answer no matter what you do, whether you solve it with projectile motion or you solve it with energy. The universe doesn't care how you figured it out. It's going to do the same thing. So hopefully that was helpful. Try to think about what the common mistakes that you had, and again, like always, go back and work the problem from scratch on your own to make sure you actually understand it. You don't really understand it until you've done it by yourself. Alright, thanks.